So, like I said, today what we're going to talk about are these things called Atwood machines. And an Atwood machine is very simply, it's when you have a pulley and you have weights on either side of that pulley. All right, we're going to we're going to look at these pulley systems when one of the weights is on flat ground, and then we'll look at it again when one of the weights is on an incline. All right. Now, it can be a little tricky to understand what exactly I'm talking about. So I have a YouTube video. Hold on. Of course, I had it up. There we go. This isn't the best video, and we don't need to hear him speak. He's kind of boring. Even more boring than me, believe it or not. But what he's got here, if I can put this on a big screen, what he's got is he's got a weight that's on a track, and then it goes. There's a string tied to it, and on the other side of that, on the other side of the pulley, there's a hanging weight. And when he lets this go, what'll happen is that the cart is going to get pulled forward because the weight is pulling it down. So, if we were in school, you guys, it would be a lot easier to see this because what I do is I have this set up in the front table, and I'll show you kind of what it looks like. I would have it set up, and I have a little car that I tie a piece of string to, and I have the string go over a pulley, and then on this side of the pulley, I take a really super tiny weight, one that's, usually I take one that's like 5 grams, really little. And I always ask everybody, do you think that the car will move when I let this go? And almost everybody says no. Okay? Now the thing is, because this car has very little friction, there's no frictional force, or very, very little frictional force opposing motion. And so even with a super tiny weight, the car actually gets pulled forward, which seems crazy. But this is the thing that you have to remember, you guys. When we're talking about forces, right? It's the forces that are in the direction of the motion that actually affect whether the object moves or not. So if I have this block, it's going to have a force that points straight down into the earth, towards the center of the earth. And that force would be equal to its weight, mass times gravity. All right? Now, this force by itself does not affect the motion from side to side of this block. Now, in real life, some of this force, right, some of that force gets translated into the force of friction. And we even have an equation for that. We know that the force of friction is equal to mu times the force that squeezes the two objects together. And we said that that was mu times the weight, mass times gravity, times the, I'm sorry, I'm blanking out for a second, times the cosine of the angle. Okay? Now, if the cosine of that angle is 90, then basically this goes away. So for this case, the force of friction would be mu times the weight. There is no angle here. All right? So it's not the weight that affects whether this block is going to slide back and forth. It's friction. All right? Now, in real life, you guys know that the bigger the weight, the more friction there is. The smaller the weight, the less friction there is. And that's because of this equation. Because the coefficient of friction times the weight ends up being friction. All right? But if there was no friction, so let's say this is a perfectly frictionless surface. I have, two superconductors floating on top of one another. There's no air resistance. It's in a vacuum. This has no bearing at all on whether this block slides or not. So if I take a car, and even though that car is really, really big, and this weight is really, really small, if there's no friction, it doesn't matter. The car is going to slide, okay? Because right now, there's only two forces that could be in the direction of motion. This block can only slide back and forth on the table, all right? So there's friction that would oppose it, and then there's an applied force that would make this block move forward, all right? Now that applied force is going to be the weight of the hanging mass. So this is my hanging mass, and the force that it's getting pulled down with is its mass times gravity. So we'll call it mh. That's just for our, own nomenclature, so we can keep it straight. So the mass of this hanging weight times gravity will be equal to this applied force. They're going to be the same. That's what's pulling on that block. So before I go any further, does everybody understand how this is going to work? The applied force here, the force that's pulling on this block is equal to the weight of this hanging mass. Does anybody have a question before I go on? Okay, no questions. So let's look at this problem. All right. In this problem, I have this mass. This mass is 5 kilograms. And then this mass is 5 grams. Okay. So the mass here, we'll call it the hanging mass. It's going to be 5 grams. If I put that in kilograms, it's 0.005 kilograms. Remember, you divide by 1,000 or you move the decimal 3 places to the left. Okay, now it says that it's on a frictionless surface. So for this problem, there is no force of friction. It doesn't exist. There's only one force pulling on these two blocks, and that is the force of gravity on this. It's the weight of this hanging mass. So what I'm looking for here in this system, I'm looking for the acceleration. Now the acceleration I can find by using the net force equals mass times acceleration. That was Newton's second law. And then we know that the net force is equal to all the forces that are going to make it accelerate minus all the forces that are trying to slow it down. Now there are no forces trying to slow it down. There's no friction here. So the net force, there's only one net force. It's this there's only one applied force. There's only one force total that will end up being the net force. It's this applied force. It's the weight of this hanging mass. So that would be 0.005 times 9.8. And that'll end up being 0.049 newtons. You can check my math just to make sure I'm right. Do I have confirmation that I'm right? Okay, I have confirmation. So then you guys, wait, did someone ask a question or?
Oh, no, I was going to say yes, but wait, so you said that there's no frictional force? So it wouldn't be 0?
Right, well, so for this problem, there's no friction, right? Yeah. And so this is what leads me right here when I do the applied force minus the opposing force. The net force is this minus 0. So anything minus 0 is going to be the anything. Right? So it's the opposing force at 0.
Wait, then where'd you get 9.8?
So the applied force is the weight of this mass that's pulling this whole system down. So gravity, right? Gravity is pulling this mass down towards the center of the Earth. And because there's nothing underneath it, right? This thing can keep going. It can slide. Unlike this can't, right? Because it's sitting on top of the table. So this one, it can pull this other weight. So as this one falls, this weight gets pulled to the right. Does that make sense?
Yeah.
Okay. And here, this is why I was trying to show you the video, even though it's not the best video, right? You can see this would be the block in my problem, and this would be the weight. And so if I back this up a little bit, for some reason it's not letting me play it in slow-mo. But if I back it up a little bit, when he lets it go, the weight that's hanging, that's the hanging mass, that pulls down, and then the block slides forward. But they have to pull together because they're on a string. So does that make sense to everybody?
Yes.
Okay. I got one answer. I'm hoping that everybody else's answer is the same. So that would be the net force, you guys. So over here, when I want to find the acceleration, I would have 0.049 newtons equals the mass. Now, is just this block moving, or are both blocks moving together? The answer would be they're both moving together. So the total mass there would be 5.005 kilograms times A. Now to get A by itself and to get rid of that 5.005, they're being divided. I mean, it's being multiplied, so I would have to divide. So those will cancel out. And then the acceleration is 0.049 divided by 5.005. Can anybody tell me what that is?
Um, 0.098.
0.098 meters per second squared. So you can see it doesn't accelerate very quickly, right? Not at all, but it does move, and it does get faster and faster and faster. Now, if there was friction here, this probably would not move. And in that video, even though this is on an air track, he doesn't turn that air track on. So he puts smaller weights on here. So he has a smaller weight there, and he lets it go. Like he's not touching it. I don't know if you guys can see that. And it's not moving, right? So he has to replace it with a heavier weight in order to get it moving. And even that heavier weight, it still doesn't move it. He has to put an even heavier weight on there. So if there's friction, right, you have to make sure that the weight of the hanging mass is bigger than the force of friction. So let's look at a problem where there's friction. We'll have the exact same problem. So I have a 5 kilogram block. Well, I should say it's almost the exact same problem. So the mass of this block is 5 kilograms. But I introduce friction now. So now there's a coefficient of friction, mu, of 0.11 between these two surfaces, between the block and the tabletop. Which means that there is going to be a frictional force. And that frictional force is going to oppose motion. It's going to try to stop this hanging weight from pulling it forward. Now I could calculate what that friction force is, because it's mu times the normal force, right? And so that ends up being 0.11 times the weight, because we're not on an incline. So that would be times 5 times 9.8. And the force of friction for this problem ends up being what? Can someone tell me? It's going to be something around 5.
5.39.
5.39. So this force of friction right here, right, that's trying to make it stop, 5.39 newtons. All right, so it's trying to make it stop. Now there's another force that's trying to pull it forward. There's a force that's trying to pull it down, and that would be the weight of this hanging mass. So that would be the applied force. The applied force would be the mass of the hanging weight times gravity. Now, I changed this mass to be 560 grams. So the applied force is going to be 0.560 kilograms times 9.8. Can someone tell me what that is?
$5.488.
Okay, so this will be 5.488 newtons. So if I'm going to redraw this little box here that's on the tabletop, you guys. For that box, there are two forces acting on it. There's friction, and then there's an applied force, right? And friction is trying to stop it. It's 5.39 newtons. This applied force is trying to accelerate it. That's 5.488 newtons. So what'll end up happening? Will the box stay still, or will it actually get accelerated?
Accelerated?
It will get accelerated, and we could figure that out. So we know that the net force are all of the applied forces minus the opposing forces, right? So our applied force, 5.488 newtons. Our opposing forces, 5.39 newtons. So our F net here, if I subtract those two, it's going to be 0.09 newtons. Do we agree with that? Did I do my math right? Yeah? Okay, I got a shake of the head. So the net force is 0.09. So now I could calculate acceleration. F net equals m times a. So 0.09 would equal, and both of these, because they're tied together with the string, they both accelerate at the same time. So that would be 5.56 kilograms times a. To get a by itself, you divide both sides by 5.56. And I do have my calculator out, so I'm going to divide them. And I get that acceleration to be 0.016 meters per second squared. So once again, it'll be a really small acceleration. Because the weight of this hanging mass is barely bigger than friction. Now, if the weight of this hanging mass was only 549 grams instead of 560, okay? If I did 549 grams, so that would be 0.549, and I timesed it by 9.8, I would get this weight instead of being 5.488. I would get it to be 5.38. If this applied force was 5.38 and the force of friction is 5.39, which of those is bigger, friction or the applied force? It would be friction, right? 5.39 is bigger than 5.38. So if I made this slightly less massive, friction is bigger than the applied force, that object doesn't move. It stays still on the table, which is what happened in that video for that professor.
Mr. Goldman?
Yeah.
So when you're doing the F net equals mass times acceleration at the end, so when you're like getting your acceleration, you're supposed to add both masses?
Yeah, you have to add both masses because they're tied together on a string, they both move together. Right? And so their masses add up.
Okay.
Yeah, and I'm glad you asked that because that is the most common mistake that students make is they forget to add those masses up. All right? Can I make this just a tiny bit trickier? Can I add just a little bit more math with a few more vectors to it? I know you're excited. I can feel it. I can feel the excitement. All right. So what if we took that block, all right, and instead of it being on a flat table, what if we put it on an inclined ramp, right? So let's do this with no friction. We'll start out with no friction. So I have a 3 kilogram block. So the mass of this block is going to be 3 kilograms. And I'm sorry, you guys, I forgot to share this with you before class, but I'll post it as soon as we're done talking. So the mass of this is 3 kilograms. Okay. Now the incline is 30 degrees. It says that there is no friction. So the force of friction here is going to be 0. There's no opposing force. There's only an applied force, a force that's pulling it up the ramp. Okay? And that applied force is going to be the weight of this hanging mass. Now we could figure that out. It says that this mass is 1 kilogram, right? So the weight of this, right, the applied force pulling down would be the mass times gravity, or that would equal 1 times 9.8. Everyone can do that math in their head. That's 9.8 newtons, okay? So I have an applied force pulling it up of 9.8 newtons. Now, is this really the only force acting on this block in the direction of motion? Or is there maybe a component of another force?
The normal?
Okay, yeah, well, close. All right. So I have the weight. Let's draw this out. I have the weight of this box, and the weight of this box is going to go straight down, right? And remember, there are 2 components of the weight that we've been looking at. One is the normal. The normal pushes straight down into the surface. So the normal isn't going to be in the direction of motion, right? Because that's not up and down. But this parallel component, right? We keep calling it the parallel force because it's the parallel component. That is in the direction of motion. Right? So remember, we have this equation for the parallel component of the force, and it's the weight, right? It's mass times gravity times the sine of the angle, where that angle matches this angle. So to find the parallel component, I'll take 3 times 9.8 times the sine of 30. And I made this a little bit messy. Let me clean it up a little. All right, that's going to be the force parallel. I'll write here force of friction equals 0. So this force parallel, that's what we're looking for. Did someone punch that in their calculator for me? Are you going to make me do it? Sine. Oh yeah, of course that's 0.5 times 9.8 times 3. Okay, so I get this force to be 14.7 newtons. So the component of the weight that's trying to pull it down the ramp, 14.7 newtons. So if I were just to look at that box, I have one force that's pulling it down the ramp with 14.7. I have one force that's pulling it up the ramp with 9.8. So this is where I said that things were going to get a little tricky. Because actually, until I look at these two forces, I actually don't know which one is the applied force and which one is the opposing force. If the parallel force is bigger than the weight of the hanging mass, it ends up being the applied force, and this object will try to slide down the ramp. If the hanging mass has a weight that's bigger than the parallel force, this ends up being the applied force, and it ends up sliding up the ramp. So this, in our example, ends up being an opposing force, because the box will slide down the ramp, and this is actually trying to get it to stop. So if there was friction, friction would point in this direction. Now there is no friction, but friction would point in that direction if there was. Does everybody understand how that works?
So basically the force applied, which was 9.8 newtons, actually becomes F parallel.
So no, well, it actually becomes the opposing force, and F parallel becomes the applied force.
Oh, so F parallel could never go like upward. It can only go backward.
Right. It can only, so the F parallel is, because it's a portion of the weight, it's always trying to make the box slide down the ramp. Always, always, always. So F parallel is always going to point down. And then the weight of this hanging weight is always, always, always going to point up the ramp. So we just have to see which one is bigger. Is the parallel force bigger than the weight of the hanging mass? Or is the hanging mass bigger than the parallel force? And here's another very common mistake, you guys. It doesn't matter which one of these boxes is heavier. In this case, it ends up sliding down the ramp and this box is heavier. But I want you to look at something. This is 3 times less massive, right, than what's on the inclined plane. But the force is only 50% smaller, right? Why? Because not all of the weight of this box is actually making it slide down. Some of it is trying to make it get forced down into the ramp. As the normal force, only a portion of the weight is making it slide down. So then for this problem, if I want to find the net force, that would be the applied forces minus the opposing forces. Now in this case, because the parallel force is bigger, that is the applied force. In this case, because the weight of the hanging mass is smaller, that's the opposing force. Plug those in my calculator, and my mental calculator gives me an answer of 4.9 newtons. I don't know if that's right. I'm guessing it's right. So then, oh, okay, good. So then the net force is also equal to mass times acceleration. So if I want to know what the acceleration of the system is, that would be 4.9 equals, and I have to add the two masses together because they're tied to a string, they're moving together. So that would be equals 4 kilograms times A. To get A by itself, I have to divide both sides by 4. And A is going to end up being 1.225. Is that right?
Yes.
Okay. Meters per second squared. So before we go on to the next example, does anybody have a question about this? No. Okay. So the next example, you guys, I'm going to do this exactly the same, but I'm going to add friction. So now I have a 3 kilogram block. It's the same block. This is still 3 kilograms. This is still 1 kilogram. This is still 30 degrees. Okay. So what that means is I didn't change anything, but I did add a coefficient of friction. I said that mu is equal to 0.15. So right now, I have a force, that's the weight of this hanging mass, okay? And that force is 9.8 newtons. It's trying to pull it up. Then I have a force that's trying to make this slide down the ramp. That's a portion of the weight. We called it the parallel force. And it was 14.7. So we know that because this force is bigger than this one, the box is going to try to slide down. Now, because the box is trying to slide down, what that means is that friction is going to point up. And in this case, I do have friction. I have friction this time. So I have to figure out what that friction force is. You have a set of equations that says friction is mu times the normal force, right? And we know that we have the weight's pointing straight down. Then we know a part of that weight, a component of that weight, is what we're calling the parallel force. It's trying to make it slide. And a component of that weight is trying to push the box into the surface, and that's called the normal force. So for all of these incline problems, the force of friction is going to be mu times the weight of the object times the cosine of the angle. So for this, the force of friction is going to be 0.15 times 3 times 9.8 times the cosine of 30. Can someone tell me what that is?
$3.819.
Okay, 3.819 newtons. So friction, always an opposing force. It's always going to go against motion, all right? So now, when I go to find F net is all of the applied forces minus all of the opposing forces. So I have one applied force. That's this component of the weight that we're calling the parallel force that's trying to make it slide down, 14.7 newtons. Then I have two opposing forces. I have the weight of the hanging mass that's trying to pull it up, and I have friction that's trying to stop it. So if I plug those three numbers into my calculator, Does anybody have an answer for that?
$1.081.
Okay. So 1.081, that'll be the net force. And then I'm running out of space, so I'll write this up here. If I want to find acceleration, net force is ma. So 1.081 equals 4, right? Because I have to add the two together. They're tied together. Times the acceleration. To get acceleration, I divide both sides by 4. And that'll be point...
0.27.
Thank you. 0.27 meters per second squared.
I have another question. Wait, for when we were doing force applied and opposing, what three numbers did we use?
Oh, okay. So the three numbers were the 14.7. This ends up being our applied force because it's the bigger of the two forces going up and down. So that'll be our applied. The weight of the hanging mass ends up being our opposing, just like in the last problem. So that didn't change. And then this time we added friction. So we added an opposing force. So when we plugged it into our equation, we have positive 14.7, because that's applied, minus 9.8, because that's trying to make it slow down, minus 3.819, because that's trying to make it slow down.
What if it was the other way? Like, because I also have it like if both of those numbers, 9.8 and 3.8, don't equal 14, then those are opposing ones?
Wait, can you ask that question again? I guess I didn't quite understand.
So if you add the opposing force of 9.8 and the frictional force, 3.8, and it doesn't equal 14.7, then
does it? So it doesn't equal it how? Like, is it bigger than, or because here
if it's less than the applied force?
Okay, so this one, when I added these two together, they were less than the applied force. So what that means is that my net force is positive, and that this box will slide down the ramp. Okay.
Oh, okay.
But here's another question that stems from your question. If for some reason these two numbers are bigger because the force of friction is bigger, what ends up happening is that this box doesn't move. All right, friction doesn't make it slide up the ramp. Friction will just stop it from going down the ramp. So this is a max amount of friction. But in order for this max amount of friction to become actualized, you have to try moving this object.
Okay.
Yeah, so if you did this problem and this answer came out negative, you would just say acceleration is 0. The box doesn't move.
Okay.
Okay.